Hey, what's up everyone? Welcome to Thermodynamics Part 2. Today we're going to go over entropy, and let's just get started with what entropy is. So entropy is a measure of molecular disorder or randomness. And a good way to look at it is if you look at like these army formations. If you see like the picture on the right, you can see how all the soldiers kind of look the same, they're all oriented the same way, and they're all, in strategic lined up spots. And as a result, their measure of randomness would be pretty low. They would have a low entropy. On the other hand, if you look at the picture on the left here, technically this isn't an army. I think this is like a riot or something. I forgot what it actually was. But these guys are not very organized. They're all, just kind of randomly placed. They're all not oriented the same way. So they would have a high entropy. Now, entropy ties into our second law of thermodynamics, which tells us that in any spontaneous reaction, the entropy of the universe increases. A spontaneous reaction is just a process that occurs with no external input on the system. So if you were to just have a system on its own, if a reaction occurred, then that reaction would have been spontaneous. And so the second law of thermodynamics is important because it tells us that entropy does not work like energy. Energy stays the same. That's what the first law of thermodynamics told us. But the second law of thermodynamics tells us that entropy is always increasing in the universe. There's always an increasing measure of randomness in the universe. Now, it's almost impossible to calculate the entropy that something has, right? If you were to stand in like a line, like a coffee shop, and you were waiting to pay, and you see like the person in front of you has to pay $4 for their drink, well, you can't know how much money they have. You just know that they have $4 less than they started off with. In a similar way, we can't measure how much entropy like a system has, but we can measure the change in entropy. And the change in entropy is determined using this equation here, where the change in standard entropy is the sum of the entropy of the products minus the sum of the entropy of the reactants. So in order to see what this equation really means, let's do a bit of practice with it. We're given the problem, determine the change in entropy for this equation here, given the following information. So we know that we're going to have to calculate the sum of the entropy of the product, so let's just do that really quickly. We know that HI has an entropy of 206.3, but remember these n's are here. And these n represent the stoichiometric ratios. And the stoichiometric ratio here is a 2. So what you would really have to do is multiply this 206.3 value times 2. So 2 times 206.3, that's 412.6. So our products here is 412.6. Let's calculate the reactants. So the sum of them would be the one for H2 and the one for I2. So 130.58 plus 116.73. Whoops, I flashed the answer. And that would get you 247.31. And so now that you have the sum of the products and the sum of the reactants, you subtract the reactants from the products. So you would do 412.6 minus 247.31. And so if I plug that into my calculator, we are going to get 165.29. And it's going to be in joules per mole times Kelvin. And that is our answer. Now, when calculating these, especially entropy and in our next unit, enthalpy, you need to be careful between positive and negative. So the positive here, the reason you put a positive is because the entropy of the system increases. A lot of times the entropy of the system will decrease, and you need to be able to make that distinction based on your calculation. So again, this reaction here has a increase in entropy, and it's going to be an increase of 165.29 joules per moles times Kelvin. And that is our answer. Let's move on to what would happen if we have like a perfect group of soldiers, right? They're all oriented the same way. They all are equally spaced. They're all positioned the same way. A perfect formation. And that perfect formation would be analogous to a perfect crystal. And as it turns out, that ties into our third law of thermodynamics, which tells us that the entropy of a perfect crystal at 0 Kelvin is 0. And think about it, it kind of makes sense. If you have identical molecules that are always symmetric, and they're at 0 degrees Kelvin, so there is no, vibrational energy, they can't move, well, their entropy would be 0. There's no sense of randomness. Everything is the same, they're not moving, and all their orientations are the same. So the third law of thermodynamics tells us that the entropy of a perfect crystal at 0 degrees Kelvin is 0. And as it turns out, perfect crystals are pretty hard. I think it is impossible to get a real perfect crystal. You can get very close, but a perfect crystal would be very, very hard to do. Now, entropy is very much dependent on positional probability. And positional probability is the number of configurations in space that yield a particular state. So, for example, in phases, you have a solid that has molecules that are tightly packed together, but in a gas, they're more spread out. So we say that the entropy in the solid is less than the entropy in a gas, because those molecules in the phase, in the solid phase, don't have as many places that they can be, right? They have to be closely packed together. But in gases, they can be in a lot more positions. So we say gas has a higher positional probability and therefore has a higher entropy. And the hierarchy of how that goes is that the entropy of a solid is less than the entropy of a liquid, which is greater than the entropy of a gas. Because again, the positional probabilities that are available to a gas is higher than a liquid, and the positional probabilities available to a liquid are higher than the solid. The second bit is the number of particles. Think about it, if you have more particles, you're going to have more positional probabilities. So if you have less particles, that's less positional probabilities, and more particles is more positional probabilities. So that means less particles is a lower entropy, and then more particles is going to be a higher entropy. Very similar to phase. Basically, when you're looking at the positional probability, you have to look at phase and number of particles. And so let's do a bit of practice with that. And I guess the thing is right here. Let's do a bit of practice. What sample has the greatest entropy at a given temperature? Let me move that out of the way. First, we have 2 moles of hydrobromic solid. And so we know that, first of all, it's a solid. So that's going to be a low entropy, but it is 2 moles. The thing about all these answer choices is that they are both 2 moles, meaning they're going to have the same number of particles. So really what we have to look at are the phases. So solid is definitely not going to have the highest entropy. Liquid is not going to have the highest entropy. What is going to have the highest entropy is the gas. So really you have to choose between C and D. But the thing about D is that you have a gas and a liquid. Remember, a liquid doesn't have as much entropy as a gas. So that means 2 moles of a gas are going to have higher entropy than 1 mole of a gas and 1 mole of a liquid. And therefore our answer would be C. And that is correct. And as it turns out, you can use these fundamentals to determine whether or not a reaction is going to have an increase in entropy or a decrease in entropy. So for example, in an increase in entropy, you can go from a solid to not only 2 particles, which increases the entropy, but one of those molecules turns a solid to a gas, right? So you go from having 1 particle on this side to 2 particles. That's an increase in entropy. And then you go from a solid to a solid and a gas. The gas is also going to work to increase the entropy. However, not all things are like this, right? Not all of them are going to have an increase in entropy. Sometimes you're going to have a decrease in entropy, where you take, well, in this case, you have 2 positional probabilities, or 2 molecules, rather. And you go from 2 particles on the left-hand side to 2 molecules on the right-hand side. So you really can't tell using that. What you have to look at are their phases. And on the left-hand side, you go from 2 aqueous to an aqueous and a solid. Remember, solid are going to have the lowest entropy. And so if you go from an aqueous to a solid, then that means you have decreased your entropy. And so if you see one, a decrease in the number of molecules from reactants to products, that's going to indicate a decrease in entropy. And if the phase changes are, a decrease in entropy, then obviously that's a decrease in entropy of the entire chemical reaction. Sometimes you're going to have these weird cases where you go from, first of all, two molecules on the left-hand side. Sorry, it's not working. Two molecules on the left-hand side to two molecules on the right-hand side. And so you can't tell with, if you just look at the molecules, whether or not it's going to be an increase or a decrease in entropy. And you go from gas and gas to gas and gas. So if you have gas plus gas to gas plus gas, that doesn't really tell you much about whether or not there's going to be an increase or decrease in entropy. So in those cases, it's ambiguous. You can't really assume whether or not you're going to have, or you can't assume what change in entropy you're going to have. But for these cases, there are, it's easily determinable whether or not entropy is going to increase or decrease. And let's just do a bit of practice regarding that idea with the last question that I have. So which of the following reactions take place with an increase in entropy under standard conditions? Well, let's go through all the four answer choices, starting with A. For A, you go from two particles on the left-hand side to two particles on the right-hand side. So that doesn't really tell us about a change in entropy. And you go from two aqueous to two aqueous. So that also doesn't tell us anything about the entropy. So A is one of those ambiguous cases. So let's just leave it there in case all the others don't check out. Let's look at B. B goes from two particles on the left-hand side to one particle. That indicates a decrease in entropy. And obviously a decrease isn't an increase, so B cannot be the right answer. C, you go from two particles to two particles. So that also doesn't tell us whether or not there's going to be a change in entropy. But what does tell us is the fact that we go from two gas to two aqueous. Remember, gases are going to have the highest entropy, so if you have a phase shift from a gas to anything else, you're by default going to have a decrease in entropy. So C cannot be the right answer, and so let's look at D. We go from two particles to one particle, therefore that's not an increase in entropy, that's a decrease. And the only thing that we're left with is A. A is our ambiguous case, so it does make sense for there to be an increase in entropy, even if we can't really see it from the start. And so I hope you learn how to use, how to predict whether or not there's going to be a change in entropy from a chemical reaction. I hope you learned something about entropy. That's all I have for this lesson. I hope to see you later on the next part or the next lesson where we're going to go over enthalpy. And so entropy is going to tie in with enthalpy, and we're going to use that a lot for the rest of thermodynamics. Well, thank you for watching, and I hope you'll join me next time.